Many people use or want to use solar panels for their home or workshop, and today we will try to deal with one of the problems when using solar panels. Summer is coming and it's getting hot, and unfortunately many of the devices that make our lives more comfortable can't be powered directly by solar panels or batteries. Fans and air conditioners and our laboratory require AC voltage, and so we decided to check how we can connect our devices. Let's see what we got, and maybe you can use our ideas at your home or in your workshop. And now let's have a start. Hello folks, this is the First Motion Lab channel, and we welcome our subscribers, as well as those who just came to see what we are doing here. Please subscribe to be kept posted. First of all, we checked which DC-AC inverters we can buy. In general, Amazon offers a huge selection of inverters, and at first glance the problem is solved by buying an inverter or two at a price of 40 or 60 euros. But it turned out that a 600 watt Purity inverter costs more than 100 euros, and a 1000 watt inverter is closer to 200. At the same time, the modified sine inverters are 2 or 3 times cheaper. But the important question is, can we use it? First, let's try to figure out what a modified sine is. First, let's remember what the modified sine signal looks like, and for this, let's go look at Google. As we can see, the modified sine signal is different from the pure sine signal, but our conditioner and fan needs it. In this video, we will try to solve this problem. Pure sine for inverters is emulated using PWM. Let's go back to Google for the answer. What do we see here? If we generate a PWM signal by constantly changing the duty cycle, we can emulate a pure sine. And for the DC-AC inverter, we need something like this signal. Let's look at the general working principle of the inverter. PWM signal from the low voltage side comes through a step-up transformer, after which it's rectified on the diode bridge and goes to high voltage transistors. The second PWM generator controls the high voltage transistors by opening and closing in pair each side of the high voltage bridge. This means that we need to make changes to this part of the inverter. It is important to remember about safety. This circuit has a common ground between the high voltage side and low voltage side. In this circuit, high voltage, in the event of a transistor breakdown, can enter to the low voltage side and harm the user. In this part of the video we will see how the PWM sign looks on the simulator. I will use a standard Arduino Uno model that is available in the Proteus. In order to run the model, we need to upload the firmware to a microcontroller. Now we will connect an oscilloscope that will show us the PWM signal. To generate a signal, we will use the timer number 1. On Arduino Uno and Arduino Nano, this pin number 10 and pin number 9. The firmware is uploaded, everything is connected. Let's see what the oscilloscope will show us. Great! Everything as we saw in the picture in the Google. The microcontroller generates 2 half waves of the PWM signal for top and bottom of the sine. On the oscilloscope we saw a PWM signal, but we would like to see how the sine that we emulate looks like. To visually see what form the signal generates our microcontroller, we will connect the simplest RC filter. For this we use two 500 ohm resistors and two 1 microfarad capacitors. We will connect filters to each of the pins so that we can see the emulation of the full sine signal on the oscilloscope. Let's run the simulation again and see how close we are to the sine signal. We see that two half waves look good, and in order to see what full scene will look like, we invert one of the channels of the oscilloscope. The RC filter did a great job and allowed us to see a pure sine signal. Now that we have had a little background on the theory, it's time to experiment. On one board I assembled an Arduino Nano and a MOSFET transistor driver. I also add a capacitor to boost the current to the gates. I used this driver. You can use another, non-inverting driver in this case. Now we have two wires to supply power to the Arduino and driver, as well as two wires to control the transistors. Let's do that, but first we need to upload our firmware to the Arduino. In order to upload the firmware file, I used Arduino. It seems to me that this is a very convenient program for working with AVR microcontrollers. Check the connection of the device, then select our file for Arduino and just press the button Program. Wait a couple of seconds, and now that we have uploaded the firmware to the Arduino, let's check what we see on the oscilloscope. A little time is needed until the Arduino boots up, and here we see the PWM signal, exactly the same as we saw in the simulation in Proteus. Folks, while I'm trying to set up the oscilloscope timing, please like this video and subscribe to our channel, it's important for us. A closer look clearly shows how the duty cycle of the pulses changes, and the dead time between turning on and turning off the transistor of the upper and lower shoulders is also clearly visible. Our controller generates a PWM with a sine waveform. We need to connect the RC filter as we did in the Proteus and make sure that everything goes as we intended. As you remember, we used 500 ohm resistors and 1 microfarad capacitors. Here we will do the same. Let's check what we got and how much the result from the simulation matched the result on the real Arduino. As you can see, the result is exactly the same. The two half waves of the sine signal looks great, and the shift of the half waves is perfect. So that everything looks like in the simulation, let's invert one ray and look at the full pure sine. It seems to me that we have done everything and are ready to see what is inside in the inverter and how we will modify it. After a bit of searching, we choose one of the inexpensive modified sun inverters available on the Amazon. In the box, in addition to the inverter, there are wires for connecting the device to the battery and car network. And just in case, we will hide the name of the manufacturer in order to avoid unnecessary questions from the manufacturer. There are 1500 watts on the device, but I have no idea what these numbers mean. If any of you know, please write in comments. The inverter has two USB ports, one socket and a switch. In general, we don't see anything unusual here. If you are going to connect such an inverter to the car network, then remember what we said earlier about the common ground at the low and high voltage sides and the possibility of damage if the transistors are damaged. Now it's time to disassemble our device and look inside to see if we can modify it. The box opens quite easily and inside everything is done quite neatly. Let's take a closer look at this device and figure out where everything is located and how it works. We can see that there are 4 low voltage transistors here. Next to them is a pulse transformer and 4 high voltage transistors. In the low voltage side, the PWM generator drives the low voltage transistors, and then the PWM signal goes to the transformer. After that, the voltage is rectified on the diode bridge and goes through the capacitor to the transistor of the high voltage part. As we know, this inverter has 2 PWM controllers for low voltage and high voltage part. Let's take a closer look at them. KA7500 is analog of the well-known TL494 PWM controller. We check the negative contact at the input of the inverter and the negative contacts of 2 PWM controllers and the negative contacts of high voltage transistors. All these contacts are closed. We learned a lot about this inverter, and now let's connect it to power to see what kind of signal we get at the output. I must once again ask you to be extremely careful when doing such work. The output of the inverter has a high voltage of 220 volts, and at the contacts of a diode bridge the voltage is 270 volts and can reach up to 300 volts. You have to be very careful, and it's best not to experiment if you are not sure what are you doing. First, we check the voltage at the output of the inverter. Excellent, 223 volts, it's good. Now connect the oscilloscope and see what the modified sign looks like. We see that the modified sign at the output of the inverter is exactly the same that we saw in the picture on Google. And now let's see how it works. Let's find the datasheet and see the purpose of the pins of this controller. This is a SMPS controller, 42 volts supply voltage, 250 milliamps output current. Let's see the pin out. Pins 11 and 8 are the collectors of the output transistors. Pins 10 and 9 are the emitters of these transistors. Pins 4 is the dead time. Pins 5 and 6, which set the frequency of the PWM signal, And the feedback in general, everything is like that of the TL494. These are the pins we need to work. All we need to change in the inverter is the output waveform, so first we need to remove the high-side PWM controller. I will try to do this as carefully as possible so as not to move other components from their places. Then clean the place where the chip was and prepare it for soldering. In this inverter, the PWM controller is powered by 12 volts, which means we can supply power to the Arduino and the MOSFET drivers without additional problems. Solder 2 wires to power the Arduino and 2 more wires to control high voltage transistors. It seems to me that this is not difficult at all. When the work is finished, it's very important to check everything very carefully and make sure that everything is soldered correctly, nothing is mixed up and there is no excess solder anywhere on the board. Also check if all the components are in the place and if there are any of them that moved during the work with hot gun. Otherwise, you will short circuit on the high voltage side. Feedback on the low side will work, but it's better not to bring it to that. Now everything is ready to start our inverter controlled by Arduino. Pay attention to the indication of this device, it seems that it doesn't cope with the work. I connected a voltmeter and the oscilloscope to the high voltage output of the inverter, and now we can see the result of our work. At the output of the inverter, we see that the output waveform is exactly the same as the output of the Arduino, which means we were able to modify a simple and inexpensive inverter for our purposes. Before we connect our device to this inverter, we need to assemble everything and then we will be ready for testing. After assembly, we will connect our inverter and we will be able to see and hear how the operation of the devices has changed. It doesn't require any explanation and, well, I say goodbye to you and hope to meet you in the next video on our channel. Goodbye, guys!